Hi, today we want to test this little AC switch mode power supply. Mains in, DC 12 volts, 1.5 amps out. We're particularly interested in how much noise there is and how that noise is made up on the output. To do this test we're going to use a Kikasui PCR 2000M AC source. That'll generate the mains to drive this. It's variable frequency, variable voltage. We're going to measure how much power this uses using this Kikasui digital power meter, KPM 1000. That'll tell us precisely how much power is going in. This will tell us how much power is coming out. Kikasui PLZ electronic load. We can look at the waveforms and the noise on this Regal DS4054 4-channel digital scope. Let's get on with the tests.
Where do we probe? Now this method seems natural, but it can give misleading results. The long probe wire on the ground return and the long wires from the power supply itself can pick up noise from within the unit which aren't really in the output. A much better way is with a probe like this with a little spring to connect the ground. There are no long wires and the probe itself is almost screened. Now you should probe here on the output terminals if you want to measure the output noise on the power supply. Or, if you're interested in discovering the source of the noise, look back and probe within the circuit. We'll have a look at one of those signals later on. Now we'll be taking screenshots and putting them on a memory stick so that you can see the results more clearly. Like this trace, for example. On this scope it's simple. Pop a stick into the scope and press a button. Done. This is a 4 gigasample per second scope. And it may show things that are too fast to worry about, things that can easily be filtered out in the final product. So we use bandwidth limiting to reduce the high frequency response of the scope. In this example, the two traces show the effect of bandwidth limiting. We've limited it to 20 megs. This is a signal without bandwidth limitation, and this is with it. Quite a difference, I think you'll agree. It's set like this. The screen shows that it's set and a little light comes on near the input socket for that channel. On this scope you can set this on a per channel basis. It doesn't have to be the whole 4 channels. So here's a waveform showing a 100 Hz ripple with lots and lots of noise coming out of the power supply. Gradually increasing the time-based speed reveals the nature of this noise. To see this in more detail I've taken screenshots. Here is the waveform with 2 milliseconds per division. As you can see the repeating pattern every 10 milliseconds, this comes from a full wave rectified 50 Hz mains. If we now select a small portion of this signal, shown on the top trace, we'll see that a window appears and a magnified version of what's in that window in the lower trace. This reveals a higher frequency component which has a period of roughly 14 microseconds. This works out to be about 70 kHz, and it's a fairly typical switching frequency of this type of unit. Speeding the time base up further shows the switching transients on the waveform. 1 microsecond per division, 100 nanoseconds per division, and finally 50 nanoseconds per division. Switching the probing point to the output leads, which we said wasn't really the best way, shows that in this case the results are pretty similar to the correct probing point. An interesting effect with this power supply was its behaviour under no load conditions. The output becomes unstable, but don't worry, that is fairly common with this type of unit. Probing further into the unit shows the charge-discharge cycle of the capacitor just after the Schottky rectifier diode on the output side. You can see the fierce charging pulse, then the gradual discharge. It's these sharp charging pulses that spell disaster for poorly designed output stages with high ESR capacitors. The capacitors eventually boil and their contents finish up all over the board. Just to satisfy ourselves that we are seeing a true picture of what is actually happening, we'll now probe directly on the output contacts with our short spring wire probe. Yep, the signals still look the same as they did before. It can be helpful to have a near field probe if you want to see more of what goes on inside a switch mode power supply, safely. Probing around you can observe several interesting signals, particularly around the ferrite transformer. And finally, we'll see how efficient our little switch mode power supply is. On the Kikasui power monitor, this is volts, frequency at mains, milliamps out, watts out, and on the Kikasui electronic load, these are the volts and the amps on the output side. We turn the output on and we see 10.7 volts, 1.5 amps. The input current is now 175 milliamps and the input power is 20 watts. So 20 watts in, 16 watts out roughly, gives an efficiency of about 80%, which is probably reasonable for a power supply like this. But that's not the whole story. We haven't taken power factor into account. That's the subject of another video. Thanks for watching. Hope you enjoyed it.
11
Bye.
fans of Cool Dude Clem's Electronic Workshop. I think it's about time for a new episode, don't you? Welcome to Cool Dude Clem's Electronic Workshop with me, your host, Cool Dude Clem. Anyway, who among you recognises this contraption that I've made? Well, those of you who have been following my videos for a very, very long time will probably remember that this is my high wattage power supply slash MOSFET driver that I've made. Uses a rewound microwave oven transformer to provide us with about 30 volts at considerable amperage. And I should really take bigger breaths before I start to speak. And there's another transformer here which powers the oscillator for flybacks and Tesla coils and things like that. Well, I've only got the oscillator in there to power up flybacks, but basically the way I use the circuit is that this transformer provides the main power. This one here is just a ballast that I can switch in and out when it's needed. So I can power up a MOSFET from this big transformer here and control the MOSFET with this little circuit here. And I can pretty much power up flybacks and things like that, except I really am not getting much power out of this transformer. Even with the primary connected directly to the mains, so there's absolutely nothing inhibiting that supply, I'm just not getting very good output from this thing. So what I'm going to do is I'm going to replace these bulky microwave oven transformers, which makes this thing weigh an absolute ton and not very efficient, and I'm going to replace that with a switch mode supply, so this thing will be lighter and be as powerful or maybe even more powerful than what I get from this transformer. Now originally what I was going to do was take these two computer power supplies I have here, modify them so they give out a little bit more voltage than they would normally do, say about 16 volts for each power supply, then connect them in series so I get about 30 volts, but then I thought, maybe that's not the best idea, putting two of these in series with higher voltage than they should be doing and at considerable amperage. Something in there, sooner or later, is gonna fail. However you say that last word. So, instead, what I'm going to do is I'm going to design and build my own switch mode power supply from scratch. And we've got some good parts in here. Got some capacitors, which I'm sure are still good. A couple of switch mode transformers there, which I'm sure at least one of those is going to come in handy. So this is the design I'm going for. Some of you may recognize the circuit. It is a half bridge. And why is it called a half bridge? Well, we've got these two MOSFETs forming half of the output stage here, and these two capacitors forming the other half of the output stage there. And these two resistors just ensure that these two capacitors get charged with the equal voltage, because you don't want more voltage on one capacitor than the other. That could really ruin your day. Now, I wanted to use a TL494 to drive the MOSFETs, but unfortunately, although that chip will be able to work this MOSFET absolutely fine, for this MOSFET here, it would be completely, absolutely useless. And I'm not going to go into exactly why that is. So, going to do a little bit of research and see if I can come up with anything better. Okay, well, done a little bit of research and I found this circuit. And this is what I'm going to base my switch mode power supply on. So here is my design. Cool Dude Clem's design. The best design in the history of designs. Well, anyway, you can see it's pretty much the same circuit. We've got the rectified mains coming in here. I haven't bothered to draw in the filtering or the rectifiers because I just really want to focus on this part of the circuit. Well, first we've got this little thing here, and I'll talk about that in just a moment. Decided to use the IR2153D chip, which is the more modern version of that chip. It has that diode built into it, so I won't have to put a diode here. So that's going to be one less part on my part list. And the output transformer, because I only need single rail output for this, I don't need dual rail output, wired it in this configuration. But I've added regulation to this circuit. That's this little simple thing down here. And what is that, you're asking? Well, I've got an op-amp, which is configured as a comparator. So we feed a little bit of the output into the non-inverting input. And by adjusting this variable resistor here, I adjust the voltage that's going into the non-inverting input. I think I said non-inverting input here, I meant... No, wait, that is non-inverting input, that's the inverting input. I'm getting myself in a bit of a muddle here, so yeah. Feeding a little bit of the output voltage into the non-inverting input, and then to the input inverting input. I mean the inverting input, I will get this right in a minute. A 10k resistor basically just controlling whatever voltage goes in there. And basically what that's going to do is when the output gets above a certain level, depending on where I've set this, the op-amp will basically turn on its output, and that's going into this opto isolator here, which is going to short out this capacitor, and if I understand the datasheet properly, that will temporarily disable the chip, and the output voltage will start to fall. And when the output voltage falls below a certain level, remember, which is set by this variable resistor here, the op-amp will basically turn off, so this opto-isolator will not be doing anything anymore, so this capacitor won't be shorted anymore, and the chip will re-enable, and the output voltage will start to rise. That is if this chip works the way I think it will. And I have experimented with putting an opto-isolator across the capacitor to make sure it has no effect on the capacitance, and it has no effect at all, so that should be okay. The datasheet specifies that I should use a MOSFET here, but I'm going to use a opto-isolator, that way I don't have to have my rectified main 0 volts connected to the ground, because that could be a little bit bad. Anyway, that's about it for this video. In the next video, I'm going to be building it and testing it. I'm actually going to build 2 of those, and I'll get into why that is later on. But for now, that's it for this video. I'll see you in the next video in a couple of days when I've got the circuit built and I'm testing it. And until next time, goodbye.